In this video, I'm going to go over AP Precalculus topics in Unit 3, Part 2, which covers topics 3.8 through 3.12. I will do a separate video over the last three topics in Unit 3 over polar coordinates. So first, tangent. We're going to find the period of tangent. So tangent has a period of pi. It's asymptotic when, so since tangent is sine of x over cosine of x, anytime our cosine of x is 0, we're going to have asymptotes. So that's going to occur at values like pi over 2, 3 pi over 2, and so on. But our period is pi. So we're finding a period with some sort of horizontal dilation. We're going to take pi and divide it by our b value. So for this one, we're going to get 8 pi. Here, if I take pi and divide it by our b, we'll get a period of pi over 4. And here I'll take pi, divide it by pi, so we get a period of 1. Next, we're going to find the location of all vertical asymptotes for each of the following functions. So first I'm going to figure out the period. So that's going to be pi over 1/2 or 2 pi for this one. Then I'm going to look at the graph of cosine, because when cosine x over 2 is equal to 0, we're going to have a vertical asymptote because we're going to be dividing by 0. So my period for this one is 2 pi divided by that 1/2. So we get a period of 4 pi. When I graph this, I'm just going to graph one cycle because that'll give me enough information. It's going to complete one cycle in 4 pi. I'm going to cut that up into 4 equal pieces. I like to cut that first one in half and then cut that in half. And we're graphing a cosine curve. So cosine crosses the y-axis at the maximum. And we get something like this. So there's different ways to write this, but I'm just going to start with this first one. So we're going to have vertical asymptotes at pi, and then it's going to repeat every 2 pi. So the period is 2 pi, which gives us that result. This graph shows a difference of 2 pi, which gets us that. So we're going to have 2 pi k, where k is an integer. Okay, we'll repeat that for this one. So the period here, the distance between our vertical asymptotes is going to be pi divided by 2 pi, or 1/2. My cosine that we're interested in looks like this. The period for cosine, 2 pi x, is 2 pi divided by our b value of 2 pi, which is 1. So we'll put our 1 there, cut that in half to get 1/2, cut that in half to get 1/4, which makes that 3/4. And then it's just the graph of cosine again. So here my first vertical asymptote is at 1/4, and then it's going to occur every 1/2. Again, where k is an integer. Now we have a general graph, and there we have all of our different pieces, but here we're just focusing on B and D. B is going to come from our period, D is going to come from our vertical shift. So this one, tangent of 0 is 0. For this one, however, it's moved down 2. So since it's moved down 2, my D is going to be -2. My period here, we're going from a -2 pi to a +2 pi. So my period is 4 pi. To find my b value, I'm going to take pi divided by that to get a b value for this one of 1/4. Here, rather than our switch, and really you're looking for the change in concavity, but I have a change in concavity here at 1, so my d is 1. My period is 1, because we're going from -1/2 to 1/2. which means my b value is pi divided by that 1, which of course is just pi. Next, we're going to be evaluating some tangent values. Now, there's a couple different ways to think about this. First, tangent is the slope. So if we can identify the slope at a specific angle, then that's going to be our tangent value. On our unit circle, using the coordinates, it's going to be the y value over the x value. Or you can just memorize the values. So for pi over 6, the coordinates on the unit circle for pi over 6 are root 3 over 2, 1/2. So when I do the y value over the x value, we end up with 1 over root 3. So we can present it as 1 over root 3, or if we rationalize it, we get root 3 over 3. Tangent of pi over 2, up at the top of the circle. Graphically, if we're looking here, that's a vertical angle. That's a vertical slope, which means this is going to be undefined. Numerically, the coordinates there are, I'll put it up here, 0, 1. So if I do the y value over the x value, we end up dividing by 0, which gets us undefined. So either way, 3 pi over 4. Graphically, 3 pi over 4 is here, so we can see that it has a slope of negative 1. The coordinates there are negative root 2 over 2, root 2 over 2. So if I do that calculation of the y value over the x value, we have the same thing, they're just opposite in sign, so we're going to get negative 1 that way as well. Here, the coordinates for 4 pi over 3 in our third quadrant are negative 1/2 and negative root 3 over 2. So when I do a negative root 3 over 2 divided by a negative 1/2, our result is a positive root 3. So in general, on our unit circle, we're going to have a slope of 0 here. Our slope's going to be undefined when it's vertical, and then the slopes increase as we go up. So this is root 3 over 3, this is 1, this is root 3, and then that translates to our other quadrants. So you have lots of options for how to calculate those tangent values, but you do need to be comfortable with the unit circle either way. In topic 3.9, we learned about the inverse trig functions. In order for our inverses to be functions, we have to restrict the range, otherwise we have multiple outputs for a single input. So for sine, when we're looking at our unit circle, our output values are going to be somewhere between negative pi over 2 and pi over 2. So we know our sine value, our y value, is going to be 0 down here, which on our typical unit circle is 3 pi over 2. But our range for sine inverse is between negative pi over 2 and pi over 2. So sine inverse of negative 1 is a negative pi over 2. Cosine, the domain is from 0 to pi. So our 1 value there, our long x value, which is a negative root 3 over 2, is going to occur at 5 pi over 6. Tangent, we just talked about tangent, but tangent has the same outputs mostly as sine. It's between negative pi over 2 and pi over 2, non-inclusive, because tangent of pi over 2 is undefined and tangent of negative pi over 2 is undefined. But here we're looking at our negative root 3 over 3, or negative 1 over root 3, which will be at negative pi over 6. Again, on our regular unit circle, we call that 11 pi over 6, but we want the one between negative pi over 2 and pi over 2. And then sine again is going to be root 2 over 2 up here at pi over 4. Next, we're going to graph the sine inverse function and then a transformation. So sine inverse, the inputs are values between negative 1 and 1. Our outputs are values between negative pi over 2 and pi over 2. So sine inverse of negative 1 is pi over 2, negative pi over 2. Sine inverse of 1 is positive pi over 2. And so we get a graph like this. We do not put arrows here because it doesn't continue past that, because if it did, it would no longer be a function. So for this one, if I'm multiplying by 3, that's a vertical dilation. So I'm just going to change the pi over 2 to a 3 pi over 2, and the negative pi over 2 to a negative 3 pi over 2. My inputs will remain the same. Next, we're going to graph arc cosine. So remember the notation. Arc cosine is exactly the same as if I were to write cosine inverse. I probably should have talked about that earlier. But these are equivalent. So arc cosine has a domain between negative 1 and 1, just like sine. But its range goes from 0 to pi. Cosine inverse of 1 is 0. So our graph looks something like that. This is going to have a horizontal dilation by a factor of 2. So my inputs are now going to be negative 2 to 2 instead of negative 1. My outputs are still going to be from 0 to pi. For my last graph, we're going to graph tangent inverse, and then we're going to do arctan pi over 2. Remember, arctan and tan negative 1 are the same thing. This one has horizontal asymptotes. Tangent has vertical asymptotes, so inverse tangent has horizontal asymptotes. For the inverse trig function, it's between negative pi over 2 and pi over 2. My graph looks something like this for tangent inverse. Here, this is going to be shifting our graph up 1, or not 1, pi over 2. So my new horizontal asymptotes are going to be at 0 and at pi. In topic 310, we dealt with trigonometric equations and inequalities. So here we've got a function k is 2 cosine theta, and we want to know where k between 0 and 2 pi is equal to negative root 3. So we'll set up our equation, and then we want to isolate the trig function. Okay, for this we're just looking for the values between 0 and 2 pi. So I'm looking for where my x value is a negative root 3 over 2. That's going to occur at 5 pi over 6 and at 7 pi over 6. Next, same range, but we're looking for where 2 sine squared theta equals sine of theta. To do this one, I'm going to go ahead and subtract that sine of theta, because now I have an equation equal to 0, which when we're dealing with quadratics is quite helpful, because then we can factor. In this case, we can factor out a common factor of sine. Zero product rule says if this is 0, the whole thing's 0. If this is 0, the whole thing's 0. So either sine of theta equals 0 or 2 sine theta minus 1 equals 0. For this equation, between 0 and 2 pi, non-including 2 pi, is going to give me a theta value of either 0 or pi. That's where my y's are 0. Here we're looking for sine of theta to equal 1/2. I add the 1 over, divide by 2. So we're looking for our y values to be 1/2, which is going to occur at pi over 6 and again at 5 pi over 6. Next, I've got 3 plus 2 cosine squared x is equal to 4. I'm going to subtract the 3 and divide by 2. Now we're going to take the square root. When you take the square root, it's important to remember that we want both plus or minus. Because if I square a positive 1/2, we'll get we'll get a positive value. But if it's a negative and I square it, we still get a positive number. This is the same as plus or minus 1 over root 2, which we're probably more used to seeing that in its rationalized form, root 2 over 2. So I'm looking for, in this case, all 4, where my x value is either positive root 2 over 2 and negative root 2 over 2. And that's going to be at all of our pi over 4s. Next, we're looking for where sine of theta is less than negative root 3 over 2. So I'm going to draw myself a circle. Okay, we're looking for our long negative x values, or y values. So those are going to occur at our pi over 3s that are closer to the y-axis. Between 0 and 2 pi, this is 4 pi over 3. This is 5 pi over 3. We want when sine, which is the y values, is less. So that's going to be everything below that on the unit circle. So we're looking for 4 pi over 3 is less than theta, is less than 5 pi over 3. We don't include those since this is a non-inclusive inequality. In topic 311, you were introduced to the secant, cosecant, and cotangent functions. Cosecant is the reciprocal of sine, secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. Since tangent is equal to sine over cosine, that means cotangent is equal to the reciprocal of that, cosine over sine. So we're going to use the properties of the reciprocal to figure out where we have some vertical asymptotes. Because anytime if we're dividing by 0, we have a vertical asymptote. So for secant, which is the reciprocal of cosine, anytime that cosine pi x over 4 is equal to 0, we're going to have a vertical asymptote. So I'm going to go ahead and graph this, just like we did with the tangent ones. My period is going to be 2 pi divided by pi over 4, which is going to give me an 8, because we'll multiply the 2 and the 4 to get 8, and the pi's cancel. So when I'm setting up my graph, we have a period of 8. Cut that in half to get 4, cut that in half to get 2, which makes that 6, and we're graphing a cosine. So just with that quick little graph, we have 2 vertical asymptotes that have been identified at x equals 2 and at x equals 6. This one, we're going to look at when sine of 3x is equal to 0, because cosecant is the reciprocal of sine. The period is going to be 2 pi over 3. We'll cut that in half to get pi over 3. Half of that is pi over 6, and then we can count 1 pi over 6, 2 pi over 6, 3 pi over 6 is equivalent to pi over 2. This time we're graphing a sine, which starts at the midline and goes up. So we have 3 vertical asymptotes that we've identified. There's obviously an infinite number of answers to these questions because the sine and cosine curves keep going. But I can say x equals 0 and x equals pi over 3. You could even throw 2 pi over 3 in there. Here, I want to look at the fact that cotangent is cosine over sine. So when sine pi x equals 0, that's my vertical asymptotes there. The period on that is going to be 2 pi over pi, which is 2. Okay, this time we're again having a sine, so we start at the midline. So we have vertical asymptotes at x equals 0, and x equals 1, and x equals 2 again if you want to throw that one in there. Next, we're going to be looking at the range of our different functions. So let's look at the graph. This is the graph of secant. Cosecant behaves very similarly. It's just kind of shifted over. The interesting thing about this graph, because cosine and sine are bounded between -1 and 1, the reciprocal is either 1 or greater or -1 and lower. Here with this 4, I have a vertical dilation by a factor of 4. Which means those asymptotes, or not those asymptotes, where we were at 1 and -1, our new range is going to be between -infinity and -4 inclusive, and from 4 up to infinity. And when we do the brackets, we include the -4 and the 4. We don't include the infinities. Here, there's two things that are going to affect it. One, we have that vertical dilation, and we have a translation. So I'm going to start with the vertical dilation, which will give me output values between -infinity and -5, and from 5 and above. Next, I'll go ahead and do that vertical translation. Okay, so I'm going to take what I got here, and I'm going to add 2. So -infinity up to -3, and then from 7 to infinity. We did some equations earlier with sine and cosine, but we can also have equations with our other trig values, or trig functions as well. So here I've got f of x is 5 plus root 3 secant x, and g of x is 3, and I want to know where we have our intersections, aka when are they equal. Okay, so I'm going to subtract 5. 3 minus 5 is 8, -2. So secant is -2 over root 3. We're just not as familiar with secant values. We are quite familiar, however, with cosine values. So cosine is the reciprocal of secant. So if we're looking for secant to be -2 over root 3, we're looking for cosine to be -root 3 over 2. That's going to occur long x's in our negatives. Will be 5 pi over 6 and 7 pi over 6. Next, we have an equation with cotangent. So my equation is going to be 4 minus 3 cotangent x. I'm going to subtract 4, divide by -3. So if we're looking for cotangent of x to equal -1, the reciprocal function is tangent. The reciprocal value is -1. In between 0 and 2 pi, that occurs in the second quadrant at 3 pi over 4, and again in the fourth quadrant at 7 pi over 4. 4, not 3. In topic 312, we were introduced to a variety of different trigonometric identities, one of which is our double angle identities. So our two double angle identities are for sine 2 theta is just 2 sine theta cosine theta, and then cosine 2 theta is cosine squared theta minus sine squared theta. There's two other variations for this one. If I substitute a 1 minus cosine squared in for that, this simplifies to 2 cosine squared theta minus 1. Conversely, if I substitute a 1 minus sine squared in for cosine squared, we get 1 minus 2 sine squared theta. I primarily stick with this one, and then if I need to convert it, I can. So we're going to be doing some matching. There's obviously way more options over here than we have here. But I'm just going to dump my values, whatever we have here, into my equation. So this is 2 theta, which means we're using the identity for cosine 2 theta, which is 2 sine theta cosine theta, which is going to simplify to 6 sine theta cosine theta. Second one, we're going to do the same thing. So this will equal -4 times that 2 sine theta cosine theta. So our correct option here is F. The cosine ones are a little bit trickier just because there's more options. I'm going to first rewrite this as a double angle. So my theta is going to be a 3 pi. So if I expand this out, we're going to have 5 times cosine squared 3 pi minus sine squared 3 pi, which is one of our options. Notice this one has these 2 values switched, which is not correct. So G is my answer for that one. 7, we're going to do the same thing. So 7 cosine, I'll rewrite that 10 pi as 2 times 5 pi. So one option is 7 times cosine squared 5 pi minus sine squared 5 pi, which is not one of our options. Okay, it looks like we're looking between this one and this one. Now I just derived these other ones here. This one, if I use that second version, where it's instead of cosine squared minus sine squared, it's 2 cosine squared minus 1. Well, then if I distribute through that 7, we're going to get option B. Also in topic 312, we were introduced to the Pythagorean identities, which I kind of already used, but let's review those. The first Pythagorean identity is that sine squared theta plus cosine squared theta is equal to 1. If you know that, you can get a lot. From this, cosine squared theta equals 1 minus sine squared theta. Sine squared theta is equal to 1 minus cosine squared theta. But then there's also some other Pythagorean identities that I can arrive at by dividing by sine squared or cosine squared. If I divide this whole statement by sine squared divided by sine squared is 1. Cosine squared divided by sine squared is a cotangent squared. And 1 divided by sine is cosecant squared theta. If I repeat that by dividing by cosine, sine over cosine is tangent, so that's going to be a tangent squared. Cosine divided by cosine is 1, and 1 divided by cosine is secant squared. So again, I would memorize this one. These 2 are easy enough to derive if needed. So with this problem here, I'm going to opt to use one of my alternate versions. I'm going to go ahead and make a replacement because I know cosecant is equal to 1 plus cotangent. So I'm going to rewrite this as cotangent squared theta minus 1 plus cotangent squared theta. 1 minus sine squared is equal to cosine squared. If I simplify this numerator, I distribute this negative, we're going to have a cotangent squared minus a cotangent squared. So in the top, we're going to have a -1. And 1 over cosine squared is secant squared. So this would be equivalent to a negative secant squared. The other identities that we learned in 312 were the sum and different identities for sine and cosine. Okay, the sum and difference identities for sine and cosine. For sine of angle A plus or minus angle B is sine of A cosine of B plus or minus cosine of A cosine of sine of B. So we have the sine and cosines of both A and B, and we just kind of have this rearrangement. If this is a plus, this is a plus. If this is a minus, this is a minus. For cosine, it's going to be cosine A, cosine B, minus plus sine A, sine B. So if this is a plus on this side, it's a minus over here. If this is a minus, this becomes a plus. Right, so with cosine, it starts cosine, cosine, cosine. So this will be cosine 3 pi over 4, cosine pi over 6. Since this is a plus, for the cosine identity, that's a minus. And then it's going to be the sine of those two angles. Okay, we'll use our unit circle. The x value at 3 pi over 4 is negative root 2 over 2. My x value at pi over 6 is root 3 over 2. My y value at 3 pi over 4 is a positive root 2 over 2. And my y value at pi over 6 is a positive 1/2. So if I multiply root 2 and root 3, we get a negative root 6 over 4. Root 2 over 4. So our final answer here is negative root 6 minus root 2 over 4. Next we have a sine. So it's sine of the first thing, cosine of the second thing. This is minus, so this is minus. Cosine of the first thing, sine of the second thing. And then again, we use our unit circle to evaluate. My y value down at 5 pi over 3 is going to be a negative root 3 over 2. My cosine of pi over 4 is a positive root 2 over 2. Sorry, yeah, this is sine. Cosine, my x value at 5 pi over 3 is going to be a positive 1/2 and a positive root 2 over 2. So we're going to end up with a negative root 6 minus root 2 over 4 again, because we're still limited to the unit circle. Our last problem is going to be very similar to our free response 4 with just trig. On the AP exam, it's going to involve both units 3 and 2. So you'll see logs, you'll see exponentials, and trig. This is just trig since that's kind of what we're working with right now. In that, parts A and B are either both going to be, A is either going to be a rewrite, and B will be a solve, or that will be switched, and the first will be 2 solves, and the second will be 2 rewrites. I did this one as 2 rewrites followed by 2 solves. So we're going to rewrite as an expression with secant appears once and no other trig functions are involved. So that kind of gives us an idea of where we're headed. One strategy that I like to use is to write all our trig functions in terms of sine and cosine. So tangent is equal to sine of x over cosine of x. Okay, so I can simplify this. Sine times sine is sine squared. In order to combine these, I want to get a denominator here of cosine. So I'm going to go ahead and multiply by 1. But a 1, that will get me a common denominator. So I can add these. And hopefully you have little alarms in your head. Go, ooh, I know what sine squared plus cosine squared is. Hopefully you think it is 1, because that is what it is. And then 1 over cosine is secant, which is excellent news since that's what we were trying to get to. For h of x, I'm going to rewrite the 1 minus cosine squared as a sine squared. Cosecant is 1 over sine. So the sine squared divided by sine just leaves me with a sine on top and a cosine on the bottom. And sine over cosine is equal to tangent. And this one said to rewrite as an expression with tangent. Our 2 solve problems. First we're going to solve for j equaling 5 pi over 3. So I'm going to set 2 arc cosine x equal to 5 pi over 3. I divide by 2, we're looking for arc cosine of x to equal 5 pi over 6. If I rewrite this, if arc cosine of x equals 5 pi over 6, then x is equal to the cosine of 5 pi over 6. Our x value at 5 pi over 6 is negative root 3 over 2. For our next one, I'm going to take 1 minus root 2 cosecant x, set that equal to 3. Then divide. So if cosecant is equal to 2 over negative root 2, we're looking for sine to equal negative root 2 over 2. We're looking at the intervals 0 to 2 pi. So our y values are negative root 2 over 2 at 5 pi over 4 and 7 pi over 4. Okay, next we're going to solve. This is the third part. It says m of x equals sine squared minus 2 cosine. Find all input values in the domain of m that yield an output value of negative 2. Fancy way of saying, where does sine squared x minus 2 cosine of x equal negative 2? Well, I'm gonna end up having to factor because I've got a quadratic and I've got a linear of a sort since they're trig. So I'm gonna take this and replace it with 1 minus cosine squared x. Next, I want to get it so that my leading coefficient is positive. So I'm going to move all of this stuff over to this side of the equation and set it equal to 0. So I'm going to add a cosine squared. I'm going to add a 2 cosine. And I'm going to subtract a 1. Then we can factor. To multiply to get a negative 3, add to get a positive 2. We have a plus 3 and a minus 1. So either cosine x plus 3 equals 0, or cosine x minus 1 equals 0. So we're looking for where cosine of x equals negative 3, or cosine of x equals 1. Cosine is bounded between negative 1 and 1, so it's never going to be root 3. It is going to be 1 at 0, and then not again until 2 pi. So I'm going to say 0 plus 2 pi k, and really I'm going to clean that up to be 2 pi k, where k is an integer. And the reason I needed to do that is because it said find all input values, which is all of those, not just bounded between 0 and 2 pi. So that was Unit 3, Part 2 review. Thank you for watching.